All right, so this whole chapter is kind of a variation on the last chapter. It's all the same reactions we saw with alkenes, but with alkynes. In last chapter, we saw that we can do hydrohalogenation of alkenes. So let's review that super quick. We said if you have an alkene and you treat it with HBr, are you going to get Markovnikov addition or AntiMarkovnikov addition? Markovnikov. So the bromine will come off the more substituted carbon. With alkynes, there's something similar. So I'll show you guys what people originally thought happened, and then we'll explore this in a little bit more detail. But let's say we've got an alkyne. We know that pi bonds can be nucleophilic. So the thought was, hey, if we have HBr around, can't the pi bond in the alkyne grab this proton, kick off bromide, give you the more substituted carbocation, after which bromide adds in to give you your final product. The problem is this isn't the true mechanism, and I'll show you why. The vinylic carbocation, meaning a carbocation off of an alkene, is not observed. In fact, this reaction was studied pretty heavily. People were trying to figure out, well, if it's not this mechanism, what mechanism is that? And oftentimes the first way chemists like to study a reaction is by studying the rate equation, right? Because we know from SN1 and SN2 reactions, you can differentiate which one it is based on the rate equation. And so their rate studies were able to help them, and they found out that the rate for this equation is equal to some little k, the rate constant, times the concentration of your alkyne, times the concentration of your acid, in this case HBr squared. So is this first order, second order, or third order? It's a third order. This is a very weird reaction. You don't often see third order reactions in chemistry. So I'll show you guys the new theory. The new theory says, well, it must involve the collision of your alkyne and two molecules of HBr. So the thought was it looks more like this, where you've got your alkyne in the center, and I'm going to show all of the carbon atoms and hydrogen atoms. And then HBr kind of sneaks in underneath, and then HBr is up above. So you see how this is three molecules colliding together? The first step involves the bromine essentially attacking in, and then this pi bond attacking out and kicking off bromide. So I'll show you guys what the transition state is thought to be. During this step, you're breaking your proton to your bromine. You're forming a new bond to the central carbon. The central carbon still has a true double bond in it and a partial third bond. We're forming a new bond. This should be a hydrogen, and you're breaking the bond to bromine. So it's a very, very unusual transition state, but essentially the alkyne's being sandwiched. And then when all is said and done, you still have the two central carbons that are a double bond. This carbon is now forming a true sigma bond to hydrogen. The old hydrogen is still attached. The bromine is coming off the more substituted carbon, and the methyl group is down here. And then in addition, you have HBr left over. But you end up with that same desired Markovnikov product that we showed before. We just know it doesn't go through a true carbocation intermediate. Yeah, so in this equation, you can tell it matches the rate because it has one molecule of your alkyne reacting with 2 molecules of HBr. So this more accurately matches the observed rate equation, and that's why they think this is the true mechanism. So this mechanism does not go through a carbocation intermediate. How many steps are there for this reaction? Just one, right? I'm showing you the intermediate, but really it's just one reaction arrow going from starting material to product. It's an unusual reaction in that regard. Does that make sense?
So when we do this, do you want us to show the intermediate, or can we just show that, like, it being sandwiched in the air?
You can just show the final product. So you were asking, do you have to show the transition state? You don't have to show it. I just show it here because people get kind of confused. They're like, well, what is this? It's more of just a sandwiching effect. So let's take a look at this in the context of some other reactions we've seen. Say I've got this starting material, which is phenylacetylene. I've got a triple bond on there and a proton hanging off the end. If I treat this with HBr in excess, we know we're going to favor this Markovnikov position, which is the red spot, over the blue spot, which is anti-Markovnikov, right? So the first product we're going to get will involve a bromine getting attached onto that Markovnikov position. However, quite often, if you've got excess, it will overshoot. And we know with HBr, it prefers to do Markovnikov addition on alkenes. Again, in this case, the Markovnikov position is still that red carbon, not that blue carbon. So with excess HBr, you can do this twice and make a dihalide. The cool thing with this is this reaction is reversible, and you can go all the way back to the starting material using what reagent?
Sodium amide.
Sodium amide in excess, right, because we need to do it twice. This time we might run into a problem, though, because if we do 2 eliminations, we also have this relatively acidic proton on there that we might deprotonate. So what should we do as a second step to reprotonate it? Add water or some sort of weak acid, right? So we can interconvert back and forth between these at will now. All right, trivia question. What sort of dihalide is this? Is it geminal or vicinal? Geminal. So this is one of the geminal dihalides we've seen. We know we can make vicinal dihalides by just doing halogenation of simple alkenes, and that's pretty straightforward. All right, so we just went through this. This is your standard Markovnikov halogenation of alkynes. We just know the mechanism varies from what we're used to. So now let's switch gears and look at the anti-Markovnikov. And let's review briefly what we saw last chapter with alkenes. We said with HBr and peroxides that we can favor the halogen going off that less substituted carbon. And with alkynes, it's similar. So let's say we've got a simple alkyne, the triple bond right there. If you treat this with HBr and peroxides, you'll end up with an alkene where your bromine can come off that less substituted carbon. And is this your E or Z alkene?
Your E.
It's the E alkene. And you can end up with one, it's the isomer, where it's the Z alkene. We're not going to get into this mechanism, just like we didn't get into it last chapter, because it goes through a radical mechanism. So you end up with the mixture of both your E and Z alkene. Because of that, this reaction is generally not done because it's a very messy reaction. It's hard to control which of the two isomers you're going to get, and even if you get one in excess, you still have to purify and remove the unwanted isomer. So if you want the E1, you got to get rid of the Z1. Does that make sense? It's pretty similar to the last chapter. Not a lot of new stuff here. So let's jump into installing alcohols now. So alcohols, we saw last chapter a bunch of different ways to install alcohols on alkenes. We'll do the same thing for alkynes. We'll start with the easy one. So let's say I want to install my alcohol in a Markovnikov fashion. What reagents would be best here?
Hydronium?
Hydronium ion or dilute acid, right? Does anybody remember the other one we can use specifically if we want to avoid rearrangement?
Oxymercuration, demercuration.
Yeah, oxymercuration, demercuration. However, if I'm a chemist and I'm given the choice, I would avoid working with mercury. So this looks a lot easier and safer for everybody, and I don't have to worry about rearrangements. So this is pretty simple to do. Let's take a look at alkynes. We'll do the same thing, a really simple alkyne. If we try to treat this with acid and water, there's no reaction. So we're kind of stuck. The weird thing with this is people try to figure out why this didn't work with alkynes, but it works with alkenes. And what they've basically figured out is the activation energy is just simply way, way, way too large. So I'll just write EA is way too large.
Is that explanation because of the triple bonds? It's much stronger?
It gets into a lot more physical organic chemistry. We're not going to get into that right now just because it gets complicated. But the problem was, in order for this reaction to occur, you had to crank up the heat so high, everything would decompose before the reaction even took place. So what's the point, right? It's kind of like turning your oven on to broil to cook a chicken. It's just going to char everything, not give you tasty chicken. All right? So what they had to find was some sort of way around this. What's a good way of getting around a reaction where you've got a super large activation energy? Catalyst, exactly. So these chemists tried to develop a bunch of catalysts, and I'll show you guys what they did. The catalyst that they ended up settling with, again, isn't the world's most environmentally friendly catalyst, but I'm going to color code everything here. So I've got a red carbon here, triple bonded to a blue carbon. Then I've got my terminal proton. They still used catalytic acid and water, but the catalyst that they settled on was mercury to sulfate. And I remember a student asked me, I think last year, how did they decide on mercury 2 sulfate as being a catalyst? They went through this highly refined process of testing everything until they found one that worked, and this is what they settled on. In the early 1900s, chemists would quite literally run thousands of reactions looking for a catalyst that worked the best, and it was just trial and error, right? They just threw something in, saw if it worked. If it did, it was a checkbox. If it didn't, it was a blank box. So this was the catalyst they settled on. And just like we saw before, we're going to favor Markovnikov hydration. So where should the alcohol go? The red carbon or blue? Red, okay. So I'm going to still make this backbone. We know we're going to convert this to a double bond. But we've got an OH here coming off that red carbon. Got our methyl group there. And both of our hydrogens will be coming off the alkene. This is referred to as an enol. And does anybody know why it's called an enol? Because it's half alkene, half alcohol, right? You merge those two together, you've got an enol. So alkene plus alcohol. Super fancy terminology here. All right, the problem is that this is really, really unstable. It doesn't like to stay at the enol form. It likes to change into a different form. So let's make a note. It doesn't prefer this form. So what happens instead is we have a second reaction take place, and this usually occurs because you've got excess acid around. So what do you think could happen if we have excess acid around? Yeah, so we've got an alkene. We saw last chapter you can protonate that pi bond, and we want to have the more stabilized carbocation. So let's show the reaction arrows. All right, so I'm going to move this down. So now this terminal carbon, the blue one here, has 3 protons. And this carbon's got a positive charge. Why is this carbocation unusually stable? Does anybody have an idea? Resonance, exactly. Told you guys it wouldn't go away. So this lone pair can dump down. And so now this red carbon and blue carbon are in the same spot, but now we've got a double bond to the position where the alcohol is at. That means that this oxygen has a positive charge. And because it's a resonance structure, I do want to bracket it to clearly show this is why it's so stable. All right, and we do have water floating around, specifically the water that was kicked off in the last step. So the water can just reach up, grab this proton off of this oxygen, kick electrons over to that oxygen to make it happier. Still have this red carbon, blue carbon, double bonded to oxygen. Blue carbon still has its 3 protons off of it. And we end up regenerating our acid. All right, so looking at this, I'll zoom out a little. What new functional group have we made? Ketone, exactly. And just like I said, the acid is catalytic, meaning it's regenerated during this whole process here. The reality is this reaction is still in equilibrium, so maybe it's 99% ketone, maybe 1% enol, but it really prefers this ketone form. What this is usually called is a keto-enol tautomerization. So let's make a note of that. Specifically, it's an acid catalyzed keto-enol tautomerization. Tautomerization is basically a fancy word for moving around protons. So if you look, we didn't change the molecular formula at all. In the first step, we added a proton, and in step 2, we removed a proton. So all we did was shuttle protons around in this reaction. So this is pretty common to see in organic chemistry, this keto-enol tautomerization. We'll see it a lot in the chapter on ketones in particular. Okay, and let's make a note of this. The ketone form is usually preferred. prefer to have two Fs or one? Is it one? I think I messed up here. There we go. That looks better. So the ketone form is usually preferred. The reaction is in equilibrium.
Jeff, there's two R's in preferred.
Yeah, I goofed up here. All right, so the reaction is equilibrium, and it's usually greater than 90% ketone. So make sure with this reaction that you clearly can show conversion from the enol all the way to the ketone. I don't expect you to draw the mechanism for the first step with the catalytic cycle and all of that. Just focus on the enol converting to that ketone. Make sense? All right, do you guys want to try a practice one? Okay. Yeah. So for the practice one, we're taking 3,3-dimethyl 1-butyne. Is treated with dilute acid and mercury 2 sulfate. What is the product? And then show the tautomerization. So just like before, you don't have to show the first step, but try to show the tautomerization afterwards. I'll give you guys a minute to work on this, but double check with your neighbor to see if you're doing everything correctly. Scoot it up here. Before you guys get too far, let's double check that we all can convert from the IUPAC name to the correct structure. Longest carbon chain is how many carbons? 4. And we have a triple bond starting at carbon 1. So that's my first 2 carbons. And I go out here, that's 3, that's 4. And I'd say, all right, 1, 2, 3, 4. I should have 2 methyl groups coming off of carbon 3. So I'm just going to tag 2 methyl groups on there. And there we go. All right, so we've got our correct starting material. I'm going to erase the numbers just so we've got some room. Just like before, I'm going to just draw dots on here for clarity's sake. During the first step, when we treat this with acid, water, and mercury 2 sulfate, where's the alcohol going to get added? To the blue or red? Blue. Okay. All right, so we're getting there. We have excess acid around. So what's the next step going to be? Yeah, the alkene will steal a proton just like we saw last chapter. Perfect. And just like we saw before, the carbocation prefers to be on the more substituted carbon, which makes sense. We've seen that previously. And we know it's resonance stabilized, so let's show the resonance structure. Specifically, we've got lone pairs here. We know this lone pair can actually dump down. This oxygen has a positive charge. And then we've got water floating around. That was our conjugate base. So what will happen in the next step? Steal the proton back, maybe? A lot of thievery going on here. Okay, so if it steals the proton back, we know we're going to get to the ketone. And this is our final product. We're going to regenerate our acid. Make sense? One of the simple things you can do in looking at these problems as a holistic picture is you can say, well, if we look at our starting material, change it to an alkane. That's going to be your new backbone. And then you're going to add a new carbon-oxygen double bond on that blue carbon. Essentially, that was the overall transformation. So it's pretty easy to predict what your products will be if I don't ask you what the mechanism is going to be. So let's try a couple of these. Let's try to quickly predict what the product will look like. So acid, H2O, mercury sulfate, and this will be a 4-point question. Then for problem 2, I'm going to give you guys a slightly different one. So when I say mercury 2 sulfate, mercury can have multiple charges. In this case, it's positive 2 because sulfate, that SO4, is a negative 2 anion. So oftentimes, for example, if I say copper 1 bromide, it means the copper has a positive 1 charge, where copper 2 bromide, copper has a positive 2 charge. All right, so first problem, we've got this red carbon, we've got this blue carbon. Which side is the Markovnikov position? Doesn't matter, right? They're equally substituted. All right, so let's take a look at these, and I'd say, all right, maybe we have one where we get a double bond, oxygen coming off that red carbon. Makes sense, right? Or we could have a second one running out of room there, where it's coming off the blue carbon. What's the relationship between these? They're the same. The cool thing is symmetric alkynes give one product. Because it doesn't matter which carbon you put the double bond on, it's the same product, right? Makes sense. All right, let's do the same thing with the bottom one. Just like before, we've got this red carbon here, we've got this blue carbon here. Are we going to get one product or two products? Two. So like I said, draw the alkane backbone. So in this case, we've got 5 carbons. We know the red carbon right here could accept the double bond, and the blue carbon remains untouched. So that could be one potential product. Or we could have one where the red one was untouched and the double bond was added on the blue position. What's the relationship between these two products?
Constitutional.
Yeah, constitutional isomers. So one thing you have to watch out for is that unsymmetric alkenes, or alkynes, excuse me, give 2 products. And that's because both the red carbon and the blue carbon are equally substituted, right? There's no difference there, so there's not a strong preference for one over the other. So do watch out for that, both on sapling and on exams. Make sense? All right, so now what we need to do is take a look at the AntiMarkovnikov hydration, and we'll get into this pretty briefly, just like we did last term, or last chapter. And we said, with alkenes, we can get an alcohol to get installed on the anti-Markovnikov position by using what reagents? Peroxide was one step, so I'll plug that in. What else are we missing?
Water. Oh, NaOH.
NaOH. So that's our oxidation step. What's in step 1? Yeah, the borane THF complex. In fact, I'm going to extend this out a bit more. Let me move this over. Okay, so just like we saw last term, this borane will dock onto the less substituted carbon, and eventually after the full oxidation process, the borane will be swapped out for an alcohol. So let's take a look at alkynes. Just like with the other process, we're going to use a boron-containing compound. However, this time I'm going to abbreviate it as R2BH. We actually can't use borane, the one we used before, and I'll talk more about that in a second. Then step 2 is exactly the same. Okay, so just like before, we said, all right, if we've got this red carbon and blue carbon, the alcohol should get installed on that blue carbon position. Make sense? So the red carbon will stay here, blue carbon's over here, and our alcohol will come off that blue carbon side. So that's our anti-Markovnikov hydration. If we look at this, though, we know we've got an enol. And just like before, we said enols really don't like to stay as enols. They like to convert into a form where we have a carbon-oxygen double bond. So when we move this all around, the carbon backbone is going to stay as is, but we're going to have a double bond there, right? What's this new functional group that we made? Aldehyde. Aldehyde. So essentially with the alkyne method, you don't go to the alcohol, you instead tautomerize all the way to the aldehyde, at least for terminal alkynes where you have a proton coming off the very end. So we're going to do that tautomerization mechanism in a second, but I did want to introduce you guys to the reagents that are used. I just had a generic R2BH. All right, so the first one, looks like this. This is diisamyl borane. Looks pretty dang bulky, right? Let's take a look at the other one. This other one is a pain to draw, so bear with me. We've got a boron bridgehead. So we've got, I'll put little circles where our carbons are. Let me fix this. So it looks kind of funky, and then the boron's got a hydrogen coming off the top. This is 9-bora bicyclo and what would the bridgeheads be? Maybe I'll change the colors so we can clearly see the carbons. So what should go in the brackets? So let's think about it this way, right? I've got my two bridge heads. Longest bridge would be 1, 2, 3. Second longest bridge would be 1, 2, 3. Third longest bridge would be one atom, specifically the boron. So this would be a 3-3-1. So 9 bora bicyclo, 3-3-1. No name. This is obviously a huge mouthful, so people just call this 9-BBN. Let me rewrite that. Why do you think they're using these wackadoodle reagents that are super bulky? Does anybody have an idea? Let's think about it this way. Let's look back up here. What do you think will happen to the enol if we use borane? The enol still has an alkene in it. It could react with a second equivalent of borane, and then all of a sudden you've got everything gummed up. These reagents are so bulky, they can only add to the alkyne. They're too bulky to add to the alkene, and so they're selectively used for this sort of reaction. So these reagents are too bulky to react with alkenes. So they're selectively used for the alkyne hydroboration. All right, I think that's where we're going to stop today. Tomorrow when we come in, what we'll do is we'll take a look at this enol to aldehyde tautomerization. It is different than what we saw before. The last one we saw, we used acid. And this one we have base, so we actually have to use a different mechanism to interconvert between the enol and the aldehyde.